Good morning class. Today we are going to discuss about the electrostatic potential energy. Now what is about the electrostatic potential energy? Whenever you are going to move the charge from one point to another, it is going to do the work, and the work is always stored in the form of potential energy. So here we have considered the charge, that is positive Q. Its electric field is in outward direction because the positive charge is always going to eject the electric field. Now let's say the charge Q naught is present at the point A and you are going to move it to the point B. So the electrostatic force experienced by this charge is given by Q naught E. Now, in order to overcome this electrostatic force, we have to apply some force. Let's say that force is F naught. This is the external force applied by us. So the work done. Work done is given by A to B, that is external force and its displacement. Because the external force, till the charge will not move, till the external force as well as your electrostatic force become equal. Now why this negative sign is used? Because their direction is opposite. So that's why we just put here the value and minus sign is ejected out in the second step. What happened? We have taken the Q naught charge outside. What we have? E dot dr. Work done is stored in the form of potential energy. And what is the U? U stands for the potential energy here, and U is the difference. There is a kind of difference because the distance is different, so that's why the potential energy difference is given, UB minus UA, and the expression one is same. Let's say if the point A is at infinity, then the potential energy at that point is always taken as 0. So work done is from infinity to point B, and because it is 0, we have placed it and we got it UB. Right. So work done from infinity to B is equals to potential, or you can say UB, right? That is equals to minus Q naught and A to B E D R. Got my words? So this is the expression for the electrostatic potential energy. Okay, now since the work done is also depends only on the initial or final position and independent of the path followed, so we can say that electrostatic potential energy is conservative in nature. And as I know, the work done by a conservative force along a closed path is always taken as 0. So here is the expression for the electrostatic potential energy. This is your expression for the electrostatic potential energy. Now let's discuss the potential energy for the various kind of system. Right. Now we will discuss the potential energy for system of 2-point charges. 2-point charges. Right. So let's discuss this expression now. Let's say we have a coordinate axis x, y, and this one is z. Now here the charges are present somewhere at point A and this is at point B. Let's say here the charge q1 is present and here the charge q2 is present. Right. Now what happened? This is the vector made over it. Here is its position is specified by the position vector r1 and its position is specified by the vector r2. So what is the displacement vector? That is r2 minus r1, initial, final minus initial. Right. Now what we have to do, as we know the work done is given by, we know the definition of the potential. Potential is work done over charge. So what will be work from here? That is charge into its potential. Got my word? So here in this case the work done will be equals to, that is charge potential at the distance r. Right. Now q1 charge is brought from infinity, because you have to do the work from infinity to certain point. q1 is brought from infinity to a point A. When this charge is going to brought from infinity to A, there is no any other charge present. So if there is no any other charges present, that means in this case the work done or the potential is going to be 0 because no work is done. Okay. listen my point clearly. Whenever you have to bring a charge from infinity to a specific point and there is no other charge present over another charge is present on it, then the work done is going to be 0. So in this case the work done is going to be 0. But if q2 is brought from infinity to point infinity from infinity to point B, the charge q1 is there, right? The charge q1 is present here now. The charge q1 is there, so the work is done. So work done is given by the charge q2 into the potential of v1, because the charge q1 possesses its own potential, that is v1. Now what is v1? v1 will be equals to, yes, that will be equals to 1 over 4 pi epsilon naught. v1 potential is due to the charge q1, so that's why we will write here q1, and the displacement vector is from a to b, so that's why r2 minus r1. Got my words? Now we just put this value here. So work done will be given by this is equals to, how much work is done? That is work done is equals to q2 into v1 की value भर देंगे 1 over 4 pi epsilon naught q1, और here it is r2 minus r1, right? So we can write it as what? 1 over 4 pi epsilon naught q1 q2, and this is r2 minus r1. Clear? And where r2 minus r1 is what? This is basically a displacement vector, of which you can write it as like this, r12. So here you can replace this expression as 1 over 4 pi epsilon naught q1 q2, and this is r12. So basically whenever you have to calculate the work done for the system that includes the two charges, you have to give the expression like this. Now as the work done is supported as a potential energy, we will replace W by U, and the expression is 1 over 4 pi epsilon naught q1 q2, and this is r12. Got my words? This is the how you will calculate the potential energy for a system having two charges. Now one thing you have to consider, that potential energy will be positive only if both charges is either positive, या तो दोनों positive हो, और either negative, या दोनों negative हो. Otherwise U is negative if one is positive or other is negative, right? So in order to make its graph, because it is inversely proportional to the distance, so here it is r, here it is u. Because it is for the case of positive, the graph goes like this. That means if the value of r is small, the value of u is going to be very, very high, right? But this possible case is only when the charges are of similar signs, right? For example, if it is minus, then it is minus, right? Otherwise, if it is positive, then both should be positive, right? If one of the two charges is going to be changed, then the potential energy is going to be negative, and the graph in that case will be like this. As the distance is going to be decreased, the potential energy is going to be maximum. But this happens only when the charges are of opposite sign. That means like this, okay? And there is a specific distance that should say, let's say r, okay? So for unlike charges, the potential energy is always going to be negative. Clear? Now next is your potential energy for three charges, or a system that having three charges, right? So let's again make a diagram. This is your coordinate axis, x-axis, y-axis, and z-axis. Let's say the point A is present here, the point B is present here, and C is somewhere here. Q1, Q2, and this is Q3. Three charges are present, and these are the position vectors that will include its positions, right? R1, R2, and R3. So here is the displacement vector from A to B. So what its value is? Final minus initial, that means R2 minus R1, right? For this, how will you write? That is R3 minus R3 minus R1. Like this you will write, na? So in this way you are going to write R3 minus R1, right? And for this one, it is R3 minus R2. In this manner you will going to write. Again, when you are going to bring the charge A from infinity to a specific point, because there is no any other charge is present over here, so the work done for the first charge is going to be 0, right? Work done for Q1 is going to be 0. I know why, I told you earlier, right? Similarly, work done for Q2, when you will write at point B, then the Q1 is present, so that's why what is the work done in that case? That is 1 to 2, that is charge Q2, and the potential of V1 as we have written earlier, that is 1 over 4 pi epsilon naught Q1 Q2 over R12. Where I have written this from? This is I have written from the previous equation, as I have calculated it earlier, right? Similarly, work done, when we write this work done on the third charge, then this is due to first charge also, and this is due to second charge also. So that's why we will write 1, 2, 3, right? So it will be equals to V1 into what? That is your Q3. This charge, this potential, this charge, this potential. So this is V2 into Q3. So what is V1 here? V1 is again 1 over 4 pi epsilon naught, that is Q1 over R12, or you can write it as R3 minus R1. R3 minus R1, like this. Okay, or you can write it as 1 over 4 pi epsilon naught. This is Q1 R13. Similarly, if you want to write V2, what it is? 1 over 4 pi epsilon naught. The charge will be Q2 because the potential is of this. So that's why we will write R3 minus R2. Got my words? So it is 1 over 4 pi epsilon naught, or in total you can write it as R2, 3. Okay, this is the position vector, and you have studied it in the earlier classes, that is of class 1. So that's why I am not going to focus so much on it, right? Now, when you will write, when you just put the value here, what you will get? You just put this value of V1 and V2 here. Okay, so you will get is, what you will get? You will get that work done by 1, 2, 3 charges, that is equals to 1 over 4 pi epsilon naught, that is Q1 Q3 over R13. Similarly, 1 over epsilon naught, that is Q2 Q3 over R23. Got my words? So total work done, whenever you are going to write the total work done, so it is included for the second one also now. So total work done, that is equals to work done by the 1 due to 2, and that is 1 to 3. So you have to just put the values, that is 1 over 4 pi epsilon naught Q1 Q2, and this is R12 plus 1 over 4 pi epsilon naught. 1, 2, 3 is this much. Now you just put the values Q1 Q3, that is R13 plus 1 over 4 pi epsilon naught Q2 Q3 R23. This is what you have. Now 1 over 4 pi epsilon naught is common, take it outside. So what you will have inside? Q1 Q2 R12 Q1 Q3 R13, and this is Q2 Q3, and this is R23. Got my word? Similarly, in order, when we write, the work done is always stored in the form of potential energy. So we are going to write it, replace it by U also. So there is no need to write the another way. You can write like this. So U will be taken as 1/2 over 1 over 4 pi epsilon naught, that is I is equals to 1 to 3. Okay, and J is equals to 1 to 3. Now why I have taken I and J? Because these 1 and 2 is going to be variable. So that's why. Okay, Qi, and this is Qj, and this is Rij. Now the question should be arise in your mind that where this half comes from, because each term is going to count it twice. For example, let's say if I is equals to 1, then J is equals to 2. If I is equals to 2, then J will be equals to 1. So each term is going to be counted twice. So that's why I included this factor half. Okay, so in this case you can write it as half, that is summation of I is equals to 1 to 3 qi. You just take it out, qi. Okay, then what you will remain with, that is j is equals to 1, 2, 3, and this is 1 over 4 pi epsilon naught, that is qj, and this is rij. You just remain with this thing, right? So potential energy in this case will be equals to half, that is your I is equals to 1, 2, 3, that is qi, and take it as vi. Just write it as v, that is the potential. So this is the calculation of the potential whenever the 3 charges would be given. Similarly, for n charges you can write the same formula. This is a generalized formula for calculating the potential energy for a system that is going to have the 3 charges. I hope you are understanding what I am saying. Now this what I am doing is, basically this is important for the numerical point of view. Derivation is not important here. This derivation is not important, but it is important from the examination point of view. I hope you are getting my words. Okay, so let's begin with next topic, that is your potential energy of an dipole in an electric field. Okay, what is the potential energy of a dipole in an electric field? As we have studied earlier, whenever the dipole is placed in an electric field, it starts rotating because of the force acting, that is known as torque. So let's say this is your uniform electric field. Okay, this is your uniform electric field, that is E. Now the dipole is placed somewhere here. Let's say dipole is placed, this is your dipole, this is minus charge, this is positive charge. The direction of dipole is from negative to positive, that is P. Now the force experienced by this charge is, that is QE, and this charge will also experience the force, that is minus QE. Okay, now this is going to make an angle theta with the electric field. Okay, now as we know, whenever the dipole is placed in an electric field, it experiences the torque, and the torque is given by, from the previous equation we just know, PE sine of theta, right? Now when it is going to rotate, it covers the displacement and it has some force, so that my work is done. Work is done to rotate it, okay, to rotate this. So work done, that is given by force into displacement. So force is in the form of torque and displacement is small, that is of d theta. Small angle is rotated. So you will write it as PE sine theta, and that is your d theta, right? This is the work done, no? Now this is the small work done. In order to calculate this total work done, what we have to do? We have to integrate it. So integrating, we have, from where you have to rotate, from theta 1 to theta 2. Okay, put the value of dw, so that is PE sine of theta d theta, right? Now because the dipole is going to be constant, electric field is going to be constant, what is going to vary? That is your sine theta. So that is going to be constant, you just take it out from the integration, and what you have, sine theta d theta. So in that you should know that what is the integration of sine theta d theta, that is your minus cos of theta, and this is theta 1, this is theta 2. So work done will be equals to, yes, that comes out to be minus PE, I have taken outside, and upper limit minus lower limit, like this. Okay, so now if, let's say, if theta 1 is going to be 90 degree, then theta 2 is going to be theta. The cos 90 is going to be 0. So we just remain with work is equals to, that is minus of PE cos of theta. And you could write it in the form of vector notation, that is minus P dot E vector. Dot is always eliminated by cos theta. Okay, now cases. Case 1. If theta is 0, that means if the dipole is placed parallel to the electric field, then what happens? This is the case of stable equilibrium. What happen? ये हमने पहले ही पढ़ लिया है. Stable equilibrium. right? Now if theta is going to be 0, just put the value here. So work done will be equals to, stored in the form of potential energy, and cos 0 is 1. So that's why u will be equals to minus of p. This is your stable equilibrium. That means potential energy in this case is negative. That indicates that the potential energy is minimum when the dipole is placed parallel to the field. If theta is 90, in that case the potential energy is going to be 0. Okay. If theta is 180 degree, it is a case of unstable equilibrium. Okay, unstable equilibrium. So in this case, when the unstable equilibrium is rise, you say that the potential energy is going to be maximum. This is maximum. This is the other cases for calculating the various kind of energy in case of dipole. So I think it's more than enough. It's sufficient. I hope you like the video, and you just go through the video again and again so that your concepts will become stronger and stronger. Thank you and have a nice day.